everybody. I thought that maybe as a kind of last event at this workshop, kind of didn't really want to do kind of a talk. I mean, I had a large collection of talks I could have given, but I didn't want to give the same talk for the fifth time or so. So we will kind of enter that.
Despite my efforts.
That's I'd rather do, let's say, a free-form kind of Q&A here, and maybe answer some, maybe not frequently, but regularly asked questions about Quantemol DB. And since I think there are some new people, maybe the first question I go to is, what is actually Quantemol DB? Short answer, it's an online database for plasma-related reactions, so both electron collisions and heavy particle collections. Collisions, and we come out here just as this website where you have a collection of reactions with the associated cross sections, rate coefficients. If you're looking for something, you can, for example, then of course you can still do this. In order to do this, you not just need to sign up to the database, and most of the data, the single data, is actually available for free, like single reactions and so on. You can, for example, then simply search it for argon, and you see the kind of the list of all the reactions we have in the database related to argon, ground states, also its excited states. And then you can, for example, I mean, if it's a bit much, you have here some filtering options, like only if you're specifically looking, let's say, for electron impact ionization, you can just say, just show me electron impact ionization, and so on. And when you then click here on the on one of the reactions, you get that here, for example, the cross section, in this case for electron impact excitation. You can download the cross section and then use it in your simulations, for example, or if you use rate coefficients, you see here the rate coefficients. Of course, this the idea of having centralized databases, that if you need to set up a chemistry set, you don't have to look through several publications. I mean, for simple things which have been investigated, you might find a chemistry set readily, but usually you have to go through several publications. So having a centralized database can speed up a bit, but when you still have to look, for example, if you have a complicated chemistry set, you will still need to kind of search for several species, click through several reactions and so on, which is still rather time consuming. So what we came up first was that we had here kind of collection of pre-assembled chemistry sets for some regularly used chemistry sets, but of course it is by not exhaustive, because in the end you can mix whatever gases you have. So it's kind of impossible to have a pre-assembled chemistry sets for every eventuality, especially since chemistry sets are usually optimized for specific process parameters, for example, specific pressure. For example, we have this argon chemistry, which is rather for low pressure, so it doesn't have the molecular ions, which are important at atmospheric pressure. On the other hand, we have this N2O2 set, which is for atmospheric pressure, which means it has a lot of species in it, which we don't need at lower pressure. And so we would have an unnecessarily large set for low pressures, which drives up your computational time. So what we then can up with, and kind of this was the first iteration of QED, so just this kind of list of reactions and this list of pre-assembled chemistry sets. And since then kind of started adding some tools which help you to collect the data you need for your chemistry set, and also maybe to optimize your chemistry set for specific conditions. And we started this actually on the website, but after a while we had more and more ideas and become more complex and kind of hit the limit of what you can realize within this browser environment. So what we then did is that we kind of launched our kind of desktop app, which you get as part of the QDB Gold subscription. And basically, when you still connects to the server to download species reaction data, but then everything else, like selecting reactions and maybe running a global model to test this, is all done locally. So there's also kind of not that much communication between your local machine and the server, which kind of heavily slowed down our browser versions of this. And here you have also the access to the pre-assembled sets. But I think what most people use it for is the dynamic set generation, where you can just select maybe arbitrary heat gases. You can also, if you're missing something, you can check whether it's here. For example, the CH, maybe, I don't know. So you simply select your feed gases, And then we kind of go through the database, starting with the feed gases and find all the reactions and species, which can originate from these initially selected species. Yeah, and then we can here go the chemistry set, select which species, which reactions to include. You can run some simple models, like, for example, the Boltzmann solver. You can run it on its own in case, for example, you have a code which needs rate coefficients as input for the Boltzmann solver, or just you can run a global model to look at get a rough idea of which species are created at specific conditions. And yeah, for example, parameter variations and so on. So, and then step to we have this analysis step, which helps you to, for example, decide which species you can take out of a set without changing the general result too much. And also maybe investigates how surface might interact with the plasma. And lastly, our PDB is quite extensive. There are necessarily some gaps. Especially when you do some well-established gases, then you can be quite confident that you get everything you need from QDB. But when you do, for example, want to investigate a new fluorocarbon, then you might get into or mix some gases which are not commonly mixed, and that we find no data, for example, for species which you can get from reactions between the radicals. So data simply doesn't exist, so it's also not in QDB. So what we're currently looking into is, and for example, what Katerina showed is via machine learning, to add some of these data estimators to this step, so you can fill the gaps. So yeah, this is generally what QDB is, what you can do with it. So it's mostly a tool to typically collect your chemistry data, test it around, and do some analysis to maybe optimize it for the process parameters, and then export it to, for example, use it in multi-dimensional simulations. And I've been talked to quite a few people, and some questions that keep popping up. And by the way, if you have any question, I'll just put them in the chat and we wait with me. Okay, so for example, one is that we have here this global model, which you can use to test your cells. Of course, one question is about what kind of discharges can you actually model or simulate with this global model. Of course, maybe the question is rather which kind of discharges can be modeled better than others, because in the end there's kind of no restriction. Of course, there are some for low temperature plasmas, so you can't have fusion plasmas with it, or maybe something like electron beam plasmas is also not really a good use case, since the type of excitation completely differs from how you do ICPs or CCPs, for example. But in general, there's kind of no limits. It's not limited to ICP or CCP. In general, you can do everything in this kind of neutral plasmas. Of course, it works better for others when it does, for example, in general, better for ICPs than for CCPs. For example, when it comes, for example, to pressure, there's no kind of official limit. There's no kind of hard limit. You say it doesn't work until the Pascal. But in general, the same with fluid models. Generally, just as the higher the pressure, the better global models or fluid models work, simply because you don't have these pesky non-local effects, which you get, for example, in low pressure CCPs, where you have electrons like going through the reactor maybe multiple times, which the fluid model or global model cannot capture. Whereas at high pressure, electron gains energy, and the need to use it is due to a collision. And so this usually works better for global and fluid models. Same is kind of with power. There's kind of no official limits, of course, and if you go too low, you simply don't get any plasma. If you go too high, you run into instabilities, but in general, there's kind of, for let's say, because in the end, let's say for normal direct dimensions of 10 by 10 centimeter roughly, we usually relatively fine from, let's say, a few watts, tens of watts to some thousand watts. It's kind of the space we have explored so far. This works quite well. Because one thing you have to consider with the power of this, for example, the difference between ICP and CCP is that the power you specify here is supposed to be the power used in the electron energy balance equation. So it's the power which is absorbed by the electrons. And for ICPs, this is a very good approximation. For CCPs, it's not that good, because in CCPs you have these high voltages which accelerate the ions and take power out of the system, which is not available to the electrons. So for, let's say you have ICP, you can simply put at 500 watt, you can put it in 500 watt, and it's relatively well approximated. Of course, you have some external losses. As for CCPs, what we usually said to people, you have to somehow estimate which part of the power actually goes into electrons, which are that, for example, also depends a lot on the frequency. And people keep asking us about it. So what we've actually added now is this kind of DC CCP mode. We can either specify just some mean sheet voltage, which is then taken into account in the energy equation, or a CCP frequency, and then kind of self-consistently estimates the sheet voltage for using the electron energy balance equation. Again, this is just a rough approximation with global model. So it doesn't capture everything. I mean, when it comes to CCPs, we usually kind of distinguish between two kinds of electron readings. You have alpha mode, which is the direction of electrons into the oscillating sheet, roughly speaking. You have gamma mode, which is secondary electrons. Well, this mostly kept by secondary electrons. And then you have also modes, which is electrons are mostly emitted by only heating in the bulk region. And currently, this current incarnation of this basically only takes care of the alpha mode. So it's probably a good approximation for low pressure, but if you get to high pressure, maybe secondary electrons and only heating become important. It will probably somewhat less, but it is at least a start so that we can calculate CCP modes a bit better with this model. Another thing that might be somewhat limiting is maybe the geometry, because even if it's a global model, you still need some geometric factors to account, for example, for loss of the surfaces. Well, what actually goes into the energy balance equation is not the power of the power density. So you need some volume to get this power density. And of course, some global models, they specifically they can specifically just type in your volume, your area. But I mean, we usually aim at making our codes as easy to use as possible. And since the vast majority of the reactors have a cylindrical symmetry, we kind of took the shortcut that you just put enter height and radius. And then we get all the geometric factors we actually use in the global model are calculated behind the scenes. So of course, if you have a non-cylindrical geometry, you can still kind of put in something which approximates your actual area or volume, but it will be a bit off. Of course, there are some questions like what we have, for example, today seen, for example, in Montu's talk today, the CCP, what do we put in as height? We put in the reactor height or the electrode gap, and usually put in the electrode gap because this is where the plasma actually is. And do we put in the whole chamber radius or just the radius of the electrode? I would also say maybe you should just put in the radius of the electrode because it's where the plasma actually is. However, this will maybe somehow miss some surface. We might get some error in the surface interaction because the wall is actually further away. So there are some limitations. Of course, this is maybe not the model itself, but just the global models that we can kind of just make rough approximations of the geometry. As said, like cylindrical geometry works best, but in general, to get back to the question, what kind of discharges can you simulate with the model? In general, apart, as I said, from maybe some special things like electron beam plasmas, we can actually use it to use approximate ICPs, microwave discharges, CCPs, and also to some extent DC discharges, which instead there's kind of no official hard limit for pressure or power. It might depend a bit on your gas mixture and if it's stable or not. But in general, you can kind of just approximate the common technological plasmas. Now, another question we get up somewhat regularly is, I mean, how large can chemistry sets get? And again, there is basically no official limit. You can take as many species or reactions as you want. Just usually it might increase the calculation time. For example, for something you get as a simple argon chemistry set, with the simplest out of the model, it just takes in seconds, maybe even less than a second. Because if you have something like C, H, F, and O in a plasma, it gives you lots of species, lots of reactions, especially in the beginning, kind of fast changing density. This can then maybe run a few minutes, but it's usually no longer than a few minutes. Because there are some special cases. We had, for example, some special cases where you had some kind of self-induced oscillations in the density. So we kind of don't reach a converged state, but the densities, maybe some densities, they just keep on oscillating a bit. And this kind of can drive the, if you find something like this can drive the calculation step up quite a bit, because you kind of simply need to retain a small time step to resolve this ongoing oscillations, but this rarely happens. So if you use kind of the normal version of the plasma, I'd say this is the longest I've seen so far. If you reach some convergence, it's maybe a few minutes. Might be a bit longer if you use the Boltzmann solver, which adds a bit. That depends a lot on the gas. It's not so much the number of reactions which slow it down, but rather you have to make a good guess for the initial EVF for Boltzmann solver. And depending on the gas, the initial guesses we kind of code it in can be further off or closer to what happens in the end. But again, this does it. So kind of a simple argon instead of 1 second can takes maybe 10 or 20 seconds or something like this maybe. Again, what else is, are there any special hardware requirements? And as you can see, I'm running it on my laptop, so the answer is no. There are ways you can run it on kind of more or less normal laptops. When you have large sets, you might maybe run into some memory issues, but mostly when you do the analysis, where you have to store a lot of information. But in general, you can just run it on your standard laptop. Another question comes up is, well, what can I do actually about the set size? Maybe a bit of history here. The set what the app does, or what this chemistry generator does. It does in this case N2H. It starts with it, puts electrons, looks what reactions do I get, what species do I get out of it, add new reactions with this new species again, look new carbon, and so on. So just an iterative loop. And in the beginnings, we didn't kind of put any limits on the number of iteration steps, which was kind of fine when we started this for the sets we tested ourselves. But then we had kind of a large addition of data, and people started mixing interesting things, which kind of led to that if you do it unlimited, you get like hundreds of species, especially, for example, if you combine C, H, F, and O, which many people do. If you do it unlimited, you get lots of CH, CHS, COs, and so on. So kind of people started complaining a bit that the sets are too large to handle. So the second step, we limited the number of reaction steps on the server side to 5, because from our experience, it's also a compromise between getting everything you need, while the set became not too large. But then people said, when I did this set, I used to get the species, now it's not, I want it back. So we in the end come up with that you can set yourself here the number of reaction steps to give you a bit more control over how large your set will become. I mean, for most cases, I think these 5 reaction sets is fine. For some more complicated cases, you might go down a bit, maybe to 4. For others, if you really want everything, you can still increase it to what you want. And yeah, even if it's too large, I mean, you can see you can either just select or deselect the species or completely delete it. The model behind it doesn't care about whether it's just deselected or deleted, but it kind of makes the tables a bit more manageable if you have large chemistry sets. I'll tell you what also came up today is how we actually handle interaction with surfaces. And the difference between, let's say, surface data and gas-phase data is the cross-section is a cross-section. It doesn't care about what's around it. Cross-section for argon ionization will always be the same on the type of reactor you are, which other gases you have in there, but the same is not necessarily true for surface coefficients. That depends a lot on what the material is. If the material has been exposed to plasma before, as I think Peter said today, when you have pulse discharges, it might change during the pulsing and so on. So we are kind of still refining this, but what we currently have is we kind of describe it here by the sticking coefficient, which simply says how many which fraction of the species with lossless surfaces and this return coefficient, which tells how many of these different species return as another species. As I said, there are no general values, so you usually need to do some kind of variation of these surface coefficients. If you have some experimental results, usually there are values that will get the experimental results. If you don't, what I like to like to do, I would like to want some different sticky coefficient just to cover different basics. And what we actually do in this analysis step, you can load up here run, and you can kind of set up here some automatic variation of it, which you can then see how the sticking or return coefficients affect the density of your species. For example, this N2H2 mixture, these NH radicals, they are almost exclusively, at least at lower pressure, exclusively created at the surfaces, but not at the gas phase. So this is rather important. So what I just set up here is actually there are these coefficients which in the end describe the production of NH by H atoms at surfaces, and then you can see how these all these different surface coefficients, which impact they have on the densities in this case of NH and H. And you also, if you have a specific target density for either or for both, you can also enter here this kind of target densities that you want to have. And then it will kind of automatically find this combination of surface coefficients, which best reproduces the desired results. The one thing that you have to say is, at least from the past models I know, basically every model handles these surface interactions a bit differently. So this might be what you need to do, but for example, whereas in gas-phase data, we have exports, for example, to console with low CFAs and so on. For the gas-phase data, it's fine. The surface data usually cannot be directly reported to other simulation software simply because surface interactions are treated somewhat differently in different software packages. But still might give you an idea of which surface coefficients you need to set in your simulation software. Yeah, and I think I'm actually almost out of time or over. So do you have any online questions or
no questions from online?
Okay, do we have any questions from the audience?
Yeah. So is it possible to couple this plasma chemistry with the suppose electromagnets or fundamental electromagnets?
Yeah, this is probably also one of the discharges, means like magnetized discharges. So this, I would say, also something which probably goes beyond the scope of a global model, because the magnets, they have kind of an influence on the particle transport of the charged particles. Yeah. Kind of what the global model assumes in order to get the estimated fluxes, that basically what you usually assume is kind of the standard diffusion profile and free diffusion more or less of the charged particles, which of course is not the case in magnetized discharges. But I think when it comes to simply for example, real test cases to see which species are created and which you might take out, but this it might actually not matter that much. So I would say that when I might have never done it myself, but I would guess that the results of the global model will probably be less accurate for magnetized discharges than they are for unmagnetized discharges. But from what I've did so far, it might actually not have that much impact on, for example, reduction in using the chemistry set. I mean, might get the same result if maybe set a bit higher power, but what you want to get from magnets are maybe somewhat larger electron densities. So the equivalent effect might actually be just increase the power to get the same electron density, because this is in the end what you need to do, for example, a reduction. So.
But for this plasma edge systems, we use electromagnets and permanent magnets to maintain the uniform density of the ions. Okay. So we basically want to we do a lot of modeling of hardware, by changing center of symmetry and number of magnets.
I said basically when it comes, for example, when you want to use, for example, the species ranking or the reduction, which are some tools you can use, for example, to determine which species you can take out of a set without changing the results too much. for what this matters is maybe not actually the power, for what it matters, for example, the electron density. So you can maybe, for example, then adjust your power bit to get the density, electron density you actually want to look at. And then use this tool to kind of optimize your chemistry set for the process parameters.
Did you find multiple return species for the same imaging species on the surface?
Yes. You can sometimes you need it, and there might actually be, for example, with the H3 plus. I would mean as a standard, we said that ions neutralize through the neutral counterparts, because H3 doesn't exist, only H3 plus. So you can go into properties for these cases. And then you can set here, for example, that it returns at one H and one H2. And this will also be a matter, for example, to include, let's say, maybe H-line products. In a case, for example, for the ions, you can have, for a standard example for IH and F, you can have SiO4 species, and then, for example, have the F and maybe also the ions return SiO4, for example, to the plasma.
You also get return species. Let's say you've got a hydrogen plasma customer type, or you might have some carbon migration through the metal wall. Can you then define the return of methane, for example?
Sorry?
Did you define the return as like methane for a pure hydrogen plasma? Because you may
Yes. In general, that's kind of when you consider, when I say in the set generation, you can choose your feed gases. It's not entirely, because what you can do, this might include also species to generate to the surfaces. When you see, for example, we have here copper in here, which is not a gas, feed gas, but which you get kind of from start to finish. So if you kind of make a gas selection here, you can simply include species which are not feed gas, but which are created at surfaces, and which do not kind of self-consistently originate from the feed gases.
Thank you.
Yes.
I have a question about the origin of the data. Is it mostly taken from experiments, mostly taken from computational sources, or a mixture of both?
We actually never looked at this, to be honest. In the data in QDB is all kind of from public sources, so from publications. But I'm not sure we've ever looked how many of these are actually measured, calculated, or simply estimated.
Yeah, and so my follow-up question is perhaps the most interesting one, I guess. What did you do if you found conflicting data?
Yeah, this is of course an interesting case. Currently, what we do is we put maybe especially for cross sections, maybe not that much of a matter, but for rate coefficients can be a great matter. I mean, for example, when we set up our machinery for rate coefficients, we sometimes found data from, say, the reaction differ by 5 orders of magnitude or so. Currently, our policy is that we put all rate coefficients on the website. If you want on the website, basically let the user decide what he wants to use. When it comes to this automatic generator, I mean, when I started it, I kind of was thinking about it if you have several rate coefficients for the same reaction, to let the user decide, but this simply became a bit too much for some chemistry sets. So the currents, what we try to do, we have kind of this kind of star ratings for reactions, which somehow give you how trustworthy someone finds it, or we find it is. So if we have more than one data set for the same reaction, we go either the one which has the higher rating, which is kind of somewhat our, and if they have the same rating, because we will not sure either currently, when it comes here, we just kind of use the, let's say, older one currently. Still, we do this basically because so far we haven't come up with a better solution. It's simply why we're doing it this way so far.
You partially look at vibrational states, but still have some vibrational states open. So let's take hydrogen to B14. Can I lump V1 to B5 and then resolve V5 to B14?
In general, what we do, we have these two options that you can use pool states, and you can use this, or you can use distinct states. What we currently do not have, and what I think is what you mean that we use both pooled and distinct states. This is something we currently do not have.
So, QBD is very heavily class-based focused, let's say, and you have also a bit of sticking coefficients in it. But is there any ambition to go towards also surface reactions? That's because you could feel also today there were some talks which were
Ambitions, yes. I mean, currently what we have, for example, for this global model, we have also a site-based surface model, which works with our global model, which we use ourselves currently, just in the terminal and so on. We do have some very scarce service data on the website. We do have the ambition to expand it. It's just finding the data is the problem. I mean, what we might add, what we currently have are some collection of some sticking coefficients, but again, then you have the problem that the same publication says, when we start, it's 1, when you let the plasma run, it's 0.1. And we have some kind of surface mechanisms, for example, action mechanisms, which have been used in Monte Carlo feature profile models or surface side models, and I think 80% of these are from our publications here currently on QDB. Again, we'd like to add more. It's just not many people actually publish these kind of detailed surface or action mechanisms. So we're going to be looking on how to kind of integrate, or I think it's kind of our circle model into, for example, this global model, so that you can kind of set up your own etching mechanism, for example, or wall mechanism, and then maybe also do some fitting to existing etch rates, so you can calibrate your coefficients. And we all have some kind of versions from this for our own use in the backend, for terminal use, so that we mostly struggle with developing a usable interface for it. And so yes, we do have the ambitions. We're just kind of looking for data and actually put it into the actual product. Cool. There aren't any other questions. I thank for your attention.